Chapter 11, the t-test for two related samples. In the previous video, we discussed the elements of this new t-test and focused on the new equations. In a repeat measure study, each individual is measured in two different treatment conditions, and we are interested in whether there is a systematic difference between the scores in the first treatment condition and the scores in the second treatment condition. A difference score, D value, is computed for each person, and the hypothesis test uses the different scores from the sample to evaluate the overall mean difference for the entire population, which is expressed as mu sub D. The hypothesis test with the repeated measures T statistic follows the same four-step process that we have used for other tests. In the complete hypothesis testing procedure is demonstrated in example 11.1, which we will walk through in just a moment. Before we get to that example, I just want to again review the elements of this particular t-test. So our t equation is as follows. T is equal to the sample mean difference minus the population mean difference over the estimated standard error of the mean difference. So the numerator, the t statistic, measures actual difference between the data, m sub d, and the hypothesis, mu sub d. Again, this is coming from taking the sum, so we have md equal to the sum of all our d scores over n, and again, d is equal to x sub 2, so our second score minus our first score. And then mu sub d is representative of the null hypothesis, and so mu sub d will always equal 0 because the null hypothesis states that there is no difference between the conditions. The denominator measures the standard difference that is expected if the null is true. Another way of thinking about what this variable represents is to state that it is the average difference between the sample mean difference, MD, and the hypothesized population mean D, mu D, which is the null hypothesis. So again, the estimated standard error of the mean difference does express the average difference between the sample average difference and the population mean difference. And that's if there truly is not any treatment effect, that if there is no difference between these groups, then this statistic or variable measures the average difference between those values if the null is true. So again, the four-step process that we've used since Chapter 8 can be applied here. And the first step of that process entails stating the research and the null hypothesis. So we're going to use example 11.1 to demonstrate the four steps. And in our text, the following information is given. Swearing is a common, almost reflexive response to pain. Whether you knock your shin into the edge of a coffee table or smash your thumb with a hammer, most of us respond with a shriek of obscenities. One question, however, is whether swearing focuses attention on the pain and thereby increases its intensity or serves as a distraction that reduces pain. To address this issue, researchers conducted an experiment comparing swearing with other responses to pain. In the study, participants were asked to place one hand in icy cold water for as long as they could bear the pain. Half the participants were told to repeat their favorite swear word over and over for as long as their hands were in the water. The other half repeated a neutral word. The researchers recorded how long each participant was able to tolerate the ice water. After a brief rest, the two groups switched words and repeated the ice water plunge. Thus, all the participants experienced both conditions, where they used their favorite swear word repeatedly or repeated neutral words. So given this information, we can now state what our research and alternative hypotheses are, and we can go through the step-by-step process to test that hypothesis given certain information provided, which include the alpha level and the sample size used. So again, this is example 11.1. It's a non-directional repeated measures t-test. And given the scenario I just presented, the null research hypothesis would state pain tolerance will not differ when individuals repeat swear words compared to when they repeat neutral words. Again, the wording in this sentence illustrates that we are using the same individuals. The alternative hypothesis would state that pain tolerance will differ when individuals repeat swear words compared to when they repeat neutral words. Now for the null hypothesis, we need to include the notation. The notation would be as follows. So the null states that the average mean difference between the two conditions would equal 0. In other words, we expect there to be no difference between those who repeat the swear words, or I should say when they repeat the swear words in comparison to when they repeat neutral words. And the alternative hypothesis would include this notation where we would state that the average mean difference is not equal to 0, that we would expect there to be some difference in the amount of pain that they are able to tolerate. So again, the null is going to say that the mean difference is going to fall in this region, and the alternative hypothesis says that it's going to fall out in the tail somewhere, demonstrating a significant difference between these two conditions. Step 2 indicates that we must set the critical regions. So we set the parameters of this particular test, and to do so we're going to need to know a couple of things. We're going to need to know if we're engaging in a one or two-tailed test. Again, this is non-directional, so it's two-tailed. We also need to know the alpha level. So alpha is equal to 0.05. And it just occurred to me that while looking at the text, there is a typo, and as many of you have noticed, there are a few typos in the text. And here it says in step 1, they've indicated alpha is equal to 0.05, which is what we're going to use. But under step 2, they indicated that alpha is 0.01, and that is clearly a mistake. We will use a 0.05 for this particular test. Next, we need to know the size of the sample, and we're told that we have 9 individuals that are going to be exposed to both conditions, and therefore we need to calculate our degrees of freedom. So degrees of freedom for a repeated measures t-test is equal to n minus 1. So we have 9 minus 1, and we get 8. And so given that information, we can now find our critical t-value. And it's going to be positive and negative because it's non-directional, a two-tailed test. So we'll use our t-distribution to find what the critical region is for this particular test. So here is our t-table. We're using a two-tailed non-directional test at alpha at 0.05. Degrees of freedom is equal to 8. So we're just going to see where these values intersect. And we find that our critical t is equal to positive negative 2.306. So we'll set the critical region negative 2.306 and positive 2.306. So we're hoping that our t-statistic falls beyond this critical region that has just been identified using our direction of the type of test, in this case non-directional test, the alpha level of 0.05, degrees of freedom equal to 8. Step 3 indicates that we now have to calculate our t-statistic, and that's going to require several calculations. So let's look at table 11.3 to see all the data that was provided. So here's the data that we were presented in table 11.3. So here in this column, this identifies the participants, and they've been labeled from A to I, again affirming that we have a sample of 9 individuals. And then we recorded their first score, which was actually the neutral condition, and then the swearing condition. So this would be x sub 1, and this is x sub 2. And so we first expose them to the neutral condition. They express neutral words while enduring the pain. And we record their level of pain on a scale of 1 to 10, which is indicated up here. So in the case of participant A, they ranked their level of pain to be 9 when they were expressing a neutral word. And then when they were experiencing pain, same type of pain, they now were using swear words, and their pain level decreased to a 7. So these two scores enable us to calculate our D scores, our difference scores. How did they differ compared to condition 2 minus condition 1? So that's the score here. So we see a -2, which is taken by taking 7, which is that participant's second score, minus 9. We get -2. The next one is -1, comes from taking 7 minus 8 is -1. So we would do that for all of the participants' first and second score and compute their difference scores. And that enables us to compute the sum of D. So down here it's already been calculated. We would take the summation of those D scores. And notice that it's a negative number. So the sum of D is equal to -18. And that should indicate something to you. What it is illustrating, the negative value is telling us that the second condition produced lower scores, because again, D is equal to x sub 2 minus x sub 1. So a negative value, again, an average negative value, indicates that the second condition overall produced smaller scores than the first condition. And once we have the sum of D, we can compute the average D score, which has been done for us down here. So we take -18, divide by n, and we get -2. So that's the average mean difference score. Again, what we're doing now is we're going to compare that, statistically speaking, to the hypothesized mean difference, which is equal to 0. But we need to convert that mean difference into a standard score, a t-statistic. So we're going to need some other calculations to do that. In particular, we're going to need our variance of the difference scores. So we learned that variance is equal to the sum of squared deviations over degrees of freedom. And we've learned since chapter 4 that there are 2 different ways of computing sum of squared deviations. At least there are 2 that we were presented in this text. And we're going to use the computational formula, which is the sum of D squared minus the sum of D squared over n. And that's the equation that we see here. And so if we replace the variables that we know, again, this has already been calculated, but I want to take you step by step. So what do we already know? Well, we know the sum of D because we needed that to calculate the mean. So let's go ahead and put that into parentheses. It's -18. We're going to square that. And we also know what n is equal to. That's equal to 9. So what we don't have is this value, the sum of D values that have been squared. And that's where this column comes in. So all we've done is taken our D values and squared them. So -2 produces +4, -1 squared is 1, so on and so forth. So we do that for all our different scores. This is similar to what we had done when we were working with x values. But now, since we're working with condition 1 minus condition 2, we have this new distribution of values, which are referred to as D values. So now we have all of our D values that have been squared, and we take the summation, and that's been calculated here. So if you take all of these scores from 4 to 16, take the summation, we get 68. And now we can enter that into our equation, and that's what we see here. So we take 18, we square it, divide by 9, and subtract it from 68. That's not what I meant to do. Excuse me. So negative 18 squared, divide by 9, subtract it from 68, and that equals, I meant to put the equals over here. And you should all get the sum of square deviation value equal to 32. And that's what was cited in the text. So now we have our average mean difference. We also have our sum of squared deviation scores for our d-distribution. And now with that information we can compute our variance. So our variance, again, this is variance of the d scores. So the variance is equal to our SS over degrees of freedom, as I had written up on the left before. So we just calculated SS, it's equal to 32. Degrees of freedom, 9 minus 1 is equal to 8. So 32 divided by 8 gives us 4. And with this value, with the variance of our d distribution, we can compute the estimated standard error of the mean difference, which would then allow us to compute our t-statistics. So we'll go on to do the final steps in step 3 by calculating our t-value. So these are the values we will need to go on to the next step, which is to calculate our estimated standard error of the mean difference. And we calculate that by taking the square root of variance over n. Our variance was equal to 4. Our n is equal to 9. So in your calculators, 4 divided by 9 and take the square root. And you should get 0.6666, or if we round and report 0.667. And with that, we can compute our t-statistic. So again, this value here represents the average difference between our sample mean difference and the hypothesized population mean difference if the null are true. Again, the null being true means that there's no difference between conditions, that regardless if you're repeating neutral words or swear words, your pain tolerance will not differ. There would be no difference between those conditions. So let's find out if the null is true. So our t-statistic is equal to the mean difference minus the hypothesized population mean difference over the estimated standard error of the mean difference. And we can replace variables. This is equal to negative 2 minus 0 and over 0.667. So in your calculators, negative 2 minus 0 divided by 0.667 is equal to, we should get negative 2.998. If we round, we would say our t is equal to negative 3.00. And now with that value, we can go back to the parameter set for this test. Again, in the center, the null states that the population mean difference is equal to 0, that the pain tolerance will not differ whether you are repeating neutral words compared to swear words. We had set the critical region at negative 2.0 to negative 2.306 and positive 2.306. Again, the critical region is represented by this blue area and the tails. If our t-value is beyond those, beyond the parameters set with the critical t, then we get to reject the null hypothesis. So where does this value reside? Well, it would be to the left over here. And again, this is set at this critical region, and so our t-value is beyond the critical region in the left tail, and it's on the negative side because again it is illustrating that using the swear words decreased the amount of pain someone was experiencing, which translates into those individuals having greater pain tolerance when they had the ability to scream out obscenities in comparison to screaming out neutral words. So again, in this case, we would express joy because we get to reject the null. The null says that we would not see any difference, that we would expect that the sample mean difference would fall in this region. It did not, therefore we get to reject the null, and at this preliminary state we would conclude that the amount of pain tolerance does differ between these two conditions. So again, step 4 says that we draw our conclusions. In this case, we would reject the null hypothesis and conclude that the results illustrate that there is a difference in the amount of pain tolerated by individuals when they are exposed to conditions of repeating neutral words compared to repeating swear words. And what I want to do next is walk you through the calculations for effect size to support that concluding statement, and then we'll end with what that conclusion would look like in an official report. So the measures of effect size include Cohen's d. So in this chapter, d is equal to, same structure as we've seen before, the mean difference over the standard deviation. And again, keep in mind that this is standard deviation of d values. So we've already calculated the variance of our d distribution, and we can use that to then calculate our standard deviation. Then we have r squared, which is the percentage of variance attributed to the treatment, and that's calculated the same as we've done in previous chapters, our t statistic squared over t squared added 2 degrees of freedom. And then we're going to compute a confidence interval. And our confidence interval is estimating the population mean difference, and we're going to use our sample data plus or minus the product of our t-value multiplied by the estimated standard error of the mean difference. And again, this is not the t-statistic that we just calculated. That t-value will come from the percentage of confidence that we've set. So again, same structure that we've used in previous chapters. So we'll begin with the calculation of Cohen's d. So again, what we had computed previously was the average mean difference from our sample data, and it was equal to -2. Our variance of the d distribution was equal to 4. So from that we can compute our standard deviation, which is needed for our d equation. We know that standard deviation is equal to the square root of our variance. So let's compute that. So it would be the square root of 4, and that's equal to 2. So now we can replace variables. The mean difference is equal to -2 over 2, which is equal to -1. And what we are now saying is that, again, the hypothesized mean difference was here in the center, represented by 0. And we're saying that if we had the ability to test everyone in the population, their mean difference, given the sample data, would equal -2. But what we're saying with our d equation is that this difference is -1 standard deviation unit. And to be technically correct, d values are always reported as positive values. And given the table of magnitude presented back in chapter 5, anything above 0.8 is considered very large in terms of difference, and effect size. So again, here, technically speaking, we would report that the difference between the hypothesized mean difference of 0 and the sample mean difference of -2 is equal to 1 standard deviation unit. It's negative because of the fact that the sample data produced a negative average. But again, our d-values are always reported as a positive value because they're simply representing how many standard deviation unit movement we see between the two values that we're comparing. So again, anything greater than 0.8 is considered very large. And again, what this is saying is that we have support to reject the null hypothesis, which is a conclusion that we did draw given our t-value in our critical region. And next, we'll calculate our r-squared, which again is the percent of variability accounted for by the treatment. So our t statistic was equal to -3. Our r-squared equation is t squared over t squared plus degrees of freedom. Replace variables. We've got -3 squared over -3 squared plus 8. So -3 squared would equal +9. We have 9 plus 8, 9 over 17. So in our calculators, and excuse me, I forgot the square here, so r squared. So r squared is equal to 9, in our calculators, 9 divided by 17, and that gives us 0.529, or we can express it as a percentage, so 52.9% of the difference is attributed to the treatment. So approximately 53% of the reason why we see a change in those individual scores, whether they're using swear words or neutral words, is due to the fact that they're experiencing different conditions. So if they weren't experiencing different conditions, then we wouldn't see a variation in scores, or a difference in conditions that don't produce a significant t-value. In this case, it was significant. So again, the reason why we see a change in scores now we can say is because of the fact that one condition was the exposure of neutral words or the use of neutral words, and in the other condition they were using swear words. So again, approximately 53% of the difference in scores is attributed to the treatment that they received. So let me just revise that. Slightly difference in scores, to be more precise, is attributed to the treatment. And then finally, so again, anything above 0.25 is considered to be a large effect. So again, another supporting statistic to affirm that rejecting the null was the accurate conclusion to draw given our t statistic of -3.00. So again, this just serves as another support for that conclusion. Next, we'll compute a confidence interval. So we'll predict what the true population mean is equal to, and we're going to use 95% as the confidence interval set. So using 95% confidence, we're going to draw what we are computing. So again, now that we know that we get to reject the null hypothesis, we would want to determine or predict what the true population mean difference is equal to using our sample data as the center of this calculated range. So we're going to calculate a value on the lower end and on the higher end, and use the statistic, the sample statistic of the mean difference, which was -2, as the basis of this range. And our equation is the population mean difference is equal to the sample mean difference plus or minus our t-value multiplied by our estimated standard error of the mean difference. Again, we're saying 95% of the time, if we were to take samples and expose them to these different conditions, the mean difference is going to fall within this particular range. And again, that leaves 5% left over in the two tails. So let's replace the variables we know. So we have the sample mean difference that equals -2 plus or minus the t-value we're going to need to get from our t-table. So we'll come back to that. And the estimated standard error of the mean difference was calculated previously and was equal to 0.667. So the only value that's missing is this t-value. And again, it derives from the confidence level and degrees of freedom. So degrees of freedom for this test is equal to n minus 1. 9 minus 1 is equal to 8. So now we're going to use our t-table to find out what that t-value is equal to. Again, it is not the t-statistic that we calculated previously. That t-value changes every time you change the confidence interval percentage, and then also is a function of the degrees of freedom. So here's our t-table. Again, computing the confidence interval is always a two-tailed process, so we're here in the second tier. Again, it's 95% confidence, that leaves 5% in the tail, which is the same as a proportion of 0.05. Degrees of freedom is equal to 8, and where these converge is the value of our t. So 2.306. And again, that was the same critical t, but it's not always going to be. Again, this was the exact same t value as it was the critical t in our test because of the fact that for our hypothesis test, we set alpha at 5% and the degrees of freedom were the same. And here we're now calculating confidence interval at 95%. So the difference between 100% and 95 is that 5%. But don't always think that it's going to be the same as your critical t. This is just an example that when they are the same, but don't always think that they're going to be the same. They may not be. For instance, had we decided to compute a confidence interval at 99%, then our t-value would have been this one over here, because we would have 1% in the tail and the degrees of freedom equal to 8. But for this case, they set 95% confidence interval, so it's the same as our t-test, which was alpha 5%. So in our equation, we can enter the t-value that we just obtained from the table, which was 2.306. And now again, we're calculating a value here and a value here, which would frame a range of 95% confidence that if we were to take all possible samples in the population and expose them to these different conditions, the average difference between the amount of pain they endured in one condition compared to the amount of pain that they, I should not say endure, I should say experienced in the second condition, that the average amount of pain would fall within this particular range that we're going to calculate. So let's take this product first and then add it and subtract it to -2. So we would revise this to state -2 plus or minus the product of those two values is equal to 1.538. And so we take -2 and add 1.538. And we take -2 and subtract 1.538. So if we take, again, we start in the center here at -2, and if we add positive 1.538, then that gives us the value on the upper end, which is equal to -0.462. And if we take -2 and subtract 1.538, that gives us the value on the lower end, and that produces -3.538. And what that range now indicates is that we're 95% confident that if we had access to the entire population and could expose individuals to both these conditions where they rated their amount of pain when they were able to repeat neutral words compared to repeating swear words, the average difference between those conditions would fall within a range of negative 3.538 to negative 0.462. And again, the center of that estimation was based on the sample data that we collected, the sample mean difference equal to negative 2. And it's important at this point to ask ourselves, is the null hypothesis represented in this range? If it is, that should give us a moment of pause and wonder if rejecting null was the correct conclusion. And in this case, we would say that it is not, because 0 would fall somewhere over here to the right of this range that we just calculated. So again, the confidence interval, right? We're saying we're 95% confident that if we had access to the entire population and test them using these two conditions, their average mean difference would fall within this range of negative 3.538 and negative 0.462. And again, 0, which is representative of the null, right, is to the right of that. So this is good. This, again, is another supporting statistic that affirms that rejecting the null was the proper conclusion to draw given our t-test that we initially started with. And now we can state how we would cite this at the end of a report. I'm going to include all the measures of effect that we just worked on, but in a normal report, the researcher would select one to include in their final statement. So again, our conclusion was to reject the null. Results indicate that the amount of pain tolerated was significantly different, and it was different because they're exposed to different conditions. And our t-test yielded a t-value with degrees of freedom in parentheses of 8, t-statistic of negative 3.00. Our d was equal to 1 standard deviation unit. Our r squared is equal to, oh, before I do that, I'm a little ahead of myself, I apologize. Before we cite our measures of effect, I need to include my probability statement. So the probability of obtaining that mean difference of negative 2, which came from the sample data, is less than our alpha of 0.05. So again, whenever we reject, the probability statement always says that it's less than 0.05. Again, our alpha was set where we were looking at this region here, and it fell into the critical region, so it has less than a 5% chance of occurring if the null were true. So apologize for overlooking that. Our d is equal to 1 standard deviation unit. R squared was equal to 0.529. And then finally, our confidence interval, 95% CI, gave us or produced a range of negative 3.538 to negative 0.462, period. So again, our conclusion would be to reject the null. Results indicate that the amount of pain tolerated was significantly different, again, different between these two conditions using the same individuals. T, reporting in parentheses degrees of freedom, in this case is equal to 8. We had a t-statistic equal to negative 3. The probability of obtaining that t-value, if the null is true, is less than a 5% chance. Our d represents that the difference between the hypothesized mu difference and the sample mean difference is 1 standard deviation unit. R squared, there's approximately 53% of the difference in scores between the treatment is due to the fact that these individuals are doing different things or being exposed to two different conditions. And we're 95% confident that if we had access to the entire population, their mean difference between these conditions would range between negative 3.538 and negative 0.462. And that concludes part 2 of chapter 11, walking through the steps of a hypothesis test for two related samples using non-directional test procedures.